What's important about these measurements is I'm going to try to explain what they mean and what this will mean as far as how do you hear this? What is the difference that it makes? So on the website now, the Trio and I think it's the VLRCT and above, we have posted under the specifications section the impulse response first, the waterfall plot, and I'm going to explain what that means, and also the impedance curve, what that means. In my opinion, these three curves, when I see them, I could give you a description of what that speaker is going to sound like pretty accurately, as if it was a review just off of those three measurements. That's only true because I have 45 years of looking at these things and knowing what does what. That's where the experience comes in. The first thing we're going to deal with, because it is the biggest and most accurate, clearest identifier of what a time and phase correct speaker measures like. And that is this right here. The input for this test looks like this. And then at this point here it terminates. That's called a step or a square wave. It's well known that a square wave, the way you create them is you have DC to light. In order to make a step, you have to include high frequencies, low frequencies, and it sounds like a pop, like a snap. So this is what comes from the amplifier and is sent to the speaker. The reason the line leans here is because that speaker doesn't go up to the megahertz in frequency response. Because it has some point where it rolls off, you get this slight lean to it. Then as it goes down here, we'll see to the end where the test ends. Now I'll draw how this happens on, in this case, a three-way. So here is the input. The first driver, that the left side of the step, will be the tweeter. And the tweeter creates this. No tweeter is perfect. It's got a little overlap, and it goes to the baseline. Then the mid-range, because it's time aligned, it starts at the same point, and it does this. And then the woofer, again, starts at the same point because they've been aligned. And you noticed all the high frequencies have been rolled off. So it has a big slope to it. Goes to the top, goes down here to the end. When you sum all these together, you get that waveform that you saw. A speaker that is not time and phase correct will look like this. We don't talk about who this is or what it is, but there is one. Here you can see that the tweeter is in phase. And as I said, because it has a very narrow range, it has a very narrow part of the spike. But now we have the mid-range, which is totally out of phase. And it goes down below the baseline where there wasn't even a signal to reproduce. But because it's wired out of phase, that causes the impulse to go south of the border here, so to speak. And then here you see the woofer is back in phase, so you see that in this case here, the woofer continues on to the bottom of the line. Now what does that mean? Well, let's take a rim shot in a drum set. A rim shot is unique in that it is reproduced in any loudspeaker by the tweeter, the mid-range, and the woofer. It is wideband. It is a wide enough bandwidth impulse that encompasses all three of those drivers. Now, what is this going to mean sonically? If you have a speaker that measures like this one here with the correct impulse, that means that that positive front is going to be in the mid-range, it's going to contribute in the tweeter, and it's going to contribute in the bass. All of them with a positive pressure in the room impacting our eardrum so that we can hear it. If you have this going on here where the mid-range frequencies are out of phase, does that mean that's so screwed up, according to what one guy reported I said at a seminar, which was not true? Is that so screwed up that it's going to make a rim shot sound like a car door closing? No, it's going to be very, very audible as the same rim shot. The differences are going to be the leading edge, the dynamics, that percussive quality of that rim shot is going to be more defined. It's going to be more truly dynamic. When I speak of dynamics, we're not talking about loudness now. I'm talking about the difference between a quiet part of a music and the maximum SPL of a transient. In that case, first-order filters, contrary to what you read, are the most dynamic because we don't have any of that energy canceled by some of the drivers putting their energy into the room in a negative wave, as a negative pressure. So what does that mean? Well, that means that this rim shot is just going to be slightly and noticeably more like that rim shot's actually happening in your room. And in our world, for people who are sensitive to this and these timing issues, that's very important. So the way you recognize a speaker that's truly time and phase correct, that's been aligned, is you look for this impulse that goes like this. It doesn't mean that it's going to, even though it looks very different, it doesn't mean that it's going to butcher it so badly you don't know it's a rim shot anymore. No. It's just articulated in a way, the texture of it and everything is just slightly more realistic, as if it could have occurred. Now, over time, if you get used to this and expect that in your recordings, the whole entire chain of our systems are time and phase correct. Cartridges are, preamps are, power amps are, wires are. Nothing has this kind of a phase reversal that we can see in a loudspeaker design. The next thing that we plot on, that we show in the specifications, is called a waterfall plot. Basically, what a waterfall plot is, you see on the very back here, you see there's about 5 or 6 lines that are actually the frequency response of the speaker. That's what that speaker measured at the listening position, and that is the same as the frequency response curve. It's why we don't show a separate frequency response curve, because it's part of the waterfall plot. At this point right here, like the 5th line that you see there, the signal, which sounds like white noise, is muted, totally muted, instantly gone. And everything that you see in the foreground coming towards me or coming towards you as you look to it, everything there is, as this energy dies down, is the way you can see how much storage is in the crossover, how many reflections because of improper the baffle board configuration. Some people call it the acoustic lens around drivers. And also, of course, ringing or sounds, that energy that is coming from the cones themselves that gives them the color of their sound. So this here is the quinto. As you can see, it dies off quite uniformly and dies off very quickly, to where this is a 24 dB here. Everything that's below 24 dB disappears into the noise of the floor of the test. Now here is a waterfall plot. Here is a waterfall plot of another speaker. In this case, a planar. As you can see, the frequency response of this is very erratic. But remember, our ears are not that sensitive to amplitude. Amplitude is pretty much a matter of tone. We want a speaker that's accurate in tones to be reasonably good in frequency response measurement. Like anything, all the parameters are important. But here, after the mute button was hit and the energy ceased to be supplied to the speaker, all of this in the foreground, all of this hash and everything is stored energy in that panel that you're hearing that was created by the speaker, was not part of the signal sent to the speaker. So you can see here, now what this sounds like is a tiny little bit of a reverb on every note. Some people like that, and that's why those speakers sell. The other thing this causes is a lot of this, if we had the impulse of this, the step function of this speaker, a lot of this would cancel. So the true dynamic snap, the dynamic contrast between quiet is muted by a lot of this energy here, because this is all energy that's working against what you hear. So an example of a speaker that has a lot of character, makes a lot of sound of its own after the signal's been removed. Then the last thing we print is the impedance plot. Not a lot to see here, but it does give you a good idea of how difficult this speaker is going to be on an amplifier. The Quinto, as you can see, like most of our products, has a very flat impedance curve. All amplifiers, even those that are claimed to be able to arc weld with, like to see a nice neutral load. What they don't like to see is huge swings where in less than an octave, you can, I don't have an example of this, but in less of an octave, you can go from 32 ohm load down to 2 ohm loads or 3 ohms or 4 ohms. This is very reactive, and this gives problems. This gives a lot of amplifiers problems. If you had a really bad resonance in the cabinet or something like that, it would show up as a notch at that frequency in the impedance curve. But for the most part, the speaker's not the most sensitive speaker in the world, but it is a very easy load to drive. And that determines a lot of what amplifier is going to sound best. So, in a nutshell, that's what those three plots mean.